The false alarm on your thrust channel. A thrust channel and alarm doesn't always mean your bearing is failing. In some cases, the hardware is perfectly healthy, but the system was incorrectly set up during commissioning. A thrust channel is a critical component of machinery protection. Its primary purpose is to ensure the rotating and non-rotating parts don't collide, by monitoring the axial position of the shaft relative to the thrust bearing faces. How thrust position is monitored. Monitoring is typically achieved through a combination of two methods. Axial thrust measurements. A transducer or probe measures the physical gap and translates it into a voltage signal. For example, a thrust channel will typically have a sensitivity of 200 mV per mil, where mil represents a thousandth of an inch of movement. An increase in movement indicates wear on the thrust bearing. Thrust bearing temperatures. Thrust bearing temperatures are often monitored using resistance temperature detectors. When the temperature increases, it is an indication that the thrust bearing is worn. In many cases, bearing temperature data is considered a better indication of the actual condition of the thrust bearing than axial positional measurements. How it is set up. The setup of a thrust channel depends on the specific machinery, but the goal is always to provide protection. There are two common methods. The centering method. The thrust collar is physically moved to the center point between the active and inactive bearings. The system is then calibrated so this central position represents the zero DC voltage. The rotor is moved to the limits of its travel within the bearing, and the voltage is noted at either extremity. Then if the alarm is 0.003 of an inch wear into the bearing, 200 mV multiplied by 3 giving 600 mV, which is added or subtracted to the voltage obtained when the rotor was at the extreme of its travel. This DC voltage now represents is the voltage that the channel must reach before the alarm. The active face method. In some equipment, like the Titan turbine, physical centering in the field is impractical because the components are buried deep inside the bearing. Instead, the unit is started and put to full load, which forces the shaft against the active thrust position. This specific voltage is then recorded and used as the zero position voltage in the control system. Then if the alarm is 0.003 of an inch wear into the bearing, 200 mV multiplied by 3 giving 600 mV, which is added or subtracted to the voltage obtained when the rotor was at the extreme of its travel. Consequences of improper setup. When a thrust channel is not set up during commissioning or is configured incorrectly, it often leads to nuisance alarms, or the equipment is not protected. If the set points do not account for the specific zero voltage of the active thrust position, the system cannot provide the approximate settings needed to give the bearing the protection it needs, potentially failing to stop the machine before catastrophic wear occurs.